Hello, honors physics students. During class, we did part A of problem 2. I'm going to go through the logic of how we did that and then also lead you through part B of problem 2. So in problem 2, we had the store sign that was hanging there by a cable, and we started by listing some information off to the side. We listed the velocity, the acceleration, and the net force. We put all that information off to the side because none of those are actually forces. Forces are always measured in newtons, and while this is important information, only forces actually go on the free body diagram. Of course, it's hanging from rest, so the velocity is 0. Nothing's changing on what it's doing, so the acceleration is 0. And the net force is 0 because sigma f equals ma. If the acceleration is 0, then the net force is 0 as well. Now, net force is measured in newtons because it is a combination of forces, but it's still not a force. Remember, it is the combination of forces, and so it's never going to go on the free body diagram. Then we established a positive direction. Arbitrarily, we picked up. Normally, of course, we choose the initial direction of motion, but the store sign isn't moving anywhere, so it really didn't matter if we called up positive or down positive. In fact, we went through the entire solution with down positive. You get the exact same answer. But we called up positive. And then we drew the actual forces. Now, we're always going to start with weight. It's always there, and it always points straight down. We calculated the weight as 910 newtons because the mass was given as 93 kilograms. It's 2 sig figs. We didn't have to show the work for this. It's just a simple calculation, and you've got 910 newtons. And then we drew the tension force. We know there's going to be a tension because there's a cable, and the cable is being stretched. Anytime you try to stretch a material, tension builds up inside the material. The cable is above the sign, and cables and strings and ropes, they can only pull, and so this tension is pointing up. So our next step was to write sigma F equals ma, Newton's second law. And here's the next step that's very, very important. Right below sigma F equals ma, we basically list each of the forces that appears on the free body diagram with the proper sign on it, reflective of what the free body diagram shows compared to the positive direction. Tension points up, we called up positive, so it's positive T. mg points down, so we called up positive, so it's negative mg. And of course they have to add up to 0, as we already set off to the side. The acceleration equals 0, the net force equals 0. Remember, net force is the combination of all forces. So it's like a tug of war. Tension up, mg down, they have to add up to 0. Simple algebra shows that T equals mg, and since the weight is 910 newtons, the tension is 910 newtons as well, which makes sense. The cable is just supporting the weights. Now we get to letter B, where it gets a little more interesting. Now it says the sign is being hoisted upwards, and there's an acceleration. So again, we start with information off to the side. Velocity, acceleration, and net force. It's moving up, so we're going to show the velocity pointing upwards. It says the acceleration is also pointing upwards, and so we draw the acceleration off to the side. Since it's moving upwards, we're going to call the direction positive. The initial direction motion is positive, and here's the acceleration vector. And sigma F equals ma is what's known as a vector equation. The direction of the acceleration is always the direction of the net force. Let me say that again. The direction of the acceleration is always the direction of the net force. That's how it works. The forces will combine as net force to create the acceleration. So if the acceleration points upwards, the net force, sigma F, also points upwards. That means when we combine the forces, something upwards has to win over something, in this case, pointing downwards. Again, we're going to start with the weight, and the weight always points straight down, and it's the same sign, so it weighs the same amount. We don't have to recalculate. We already know it weighs 910 newtons. Now, as you draw this vector, really try to make it the same length as you did in part A, because it is the same weight, right? And so it should be the same length. Whenever we draw the lengths of the vectors, it should be sort of reflective of how much it is, the proportionality to other vectors. There's also going to be a tension of the cable, and we know that the cable is above it, so we know the tension is going to point up, but how should we draw the length of that tension vector compared to the weight? Well, it certainly can't be equal, otherwise we'd be right back at the situation in part A where the net force is 0, and that's not what's happening here. So here's where we use the information off to the side. We again know the net force points upwards because the acceleration points upwards. That means that the upwards pointing force has to win, again like a tug of war. So in this case, we know the tension pointing upwards has to win over the weight. There's more force up than there is down, so we'll draw the tension force longer. If we just do it the same as before, it would indicate that the net force is 0, but that's not what's happening here. The tension has to beat the weight. How much longer is it? Well, we don't exactly know just yet. We'll figure that out soon, but it should be noticeably longer so anyone can see that this vector is longer than this vector. Okay, so we did information off to the side, we did our positive direction, we did the actual forces on the free body diagram. The next step is always to write sigma F equals ma. And the step after that is always to list the forces shown on the free body diagram with their proper sign. We're calling up positive because it's moving upwards. Tension is pointing upwards, so we list it as positive t. mg is pointing downwards and upwards in the positive direction, so we list it as negative mg. The right-hand side is not 0 like it was in part A, and so we just say it equals ma. So again, all we did was we looked at the free body diagram, we compared the direction of the force to the positive direction, compared the direction of the force to the positive direction, and put the signs on them. This takes care of the direction of the forces, and so then when we solve for any part of this problem, we're going to be getting the magnitude of the force, which is really all we ever care about. So at this point, as always, we're going to rearrange, so go ahead and pause the video, just rearrange that for tension, and you can go ahead and put your numbers in. So simple algebra shows that tension equals mg plus ma, and then if you want to get a little bit fancy, if you want to pull a mass to the outside, right, you can factor out mass times g plus a. G is, of course, 9.8 meters per second squared. The acceleration here is given as 0.25 meters per second squared. Or, if you don't like this, you can always just back up a step. We already know what the weight is. It's 910 newtons. And then just add that to the mass times the acceleration. In any event, we should be getting 930 newtons, which makes sense because we originally assumed that the tension would be larger than the weight because, again, the net force points upwards. The upwards pointing force has to win. And so in this case, the tension certainly is larger than the weight. Now, if you just back up one step here, where it says T equals m times g plus a, it seems like we may have developed an equation for tension. Well, that's not really true. It turns out there is no equation for tension. Tension is a reaction force. It will do whatever is necessary to make whatever is happening. So if you pull harder on the cable, the tension will be harder. If you pull less on the cable, the tension will be less. Tension doesn't have a set value, like in this case weight does, because it's just the weight of the object, m times g. And so this is not the equation for tension, it's just what happens in this particular problem. For example, in letter A, tension happened to be equal to weight. In other situations, tension will be less than the weight. In some cases, they'll have no relation to weight whatsoever. There is no equation for tension. Sorry if you don't like that, that's just the way it is. It depends on how hard the string is being pulled. One more point to note here is that it looks like we're adding accelerations when we write g plus a. I want to be very, very clear about this. We are not. I can understand why you would think so, because it sort of looks like we're adding g plus a. That's what the algebra says, but that's not what we're doing. If we go back to Newton's second law, it says sigma f equals ma. Sigma, of course, means to add things together, right? And so we're adding forces. As a result of adding the forces, we get an acceleration. Forces cause accelerations. In this case, really, the net force causes the acceleration. And that's what this step over here says. T minus mg, that's the net force. Adding those forces together produces an acceleration. The algebra looks like we're adding accelerations, but that's very confusing to some students. If you were later to be asked a problem where you had to do some calculations with kinematics, you might be saying to yourself, well, what's the real acceleration? Well, the real acceleration is what's given. It's 0.25 meters per second squared. They're not lying to you. That is the acceleration of the object. So while it looks like we're adding g plus a, we're not, okay? And so if that's going to bother you, if you think that you're going to have to add 9.8 to the actual acceleration, make sure we don't do that. And if that bothers you, then don't even write this step. Just write it as t equals mg plus ma, and you can stop there. When we factored out the mass, that's just something to do for the algebra to make it a little bit easier when you plug the numbers in. So again, to be very, very clear, the acceleration is 0.25 meters per second squared. You don't have to add 9.8 or subtract 9.8. You'll never have to do that. The acceleration is what's given in the problem.